Okay, number 5. A child watches his toy train move along a circular track. He finds out that the train makes 10 complete revolutions around the track every minute. Every minute. The question is, what is a train's frequency? Well, frequency is the number of revolutions per minute. Well, we could have revolutions per minute, or in this case, we want revolutions per second. So we're going to convert this. 1 minute is equal to 60 seconds. Okay. And so we end up with 10 divided by 60, or 0.167 to 3 significant figures, revolutions per second. So that is the frequency. And then it asks for the period. The period is 1 over the frequency, 1 over 0.167 revolutions per second. We take the reciprocal of that, and we get 6 seconds, and it's really per revolution, or we just say the period of 6 seconds. Okay. Okay, let me erase this. Okay, number 6. 2 objects are 45 centimeters apart. What is the gravitational attraction between them? Okay, I won't solve this because it's relatively easy, but basically this is just an application of Newton's gravitational law, and you simply plug into these and you find out what the number is. Remember, when they said everything has to be in MKS units, metric units, so when they say R is when they say it's 45 centimeters, we have to convert that to meters. So remember to convert everything to meters, and the answer should be something like 1.2 times 10 to the minus 7 newtons. Okay. All right. Okay, number 7. Okay. How long does it take Saturn to make one orbit around the Sun? And it gives the mass of the Sun. The mass of the Sun is 2 times 10 to the 30 kilograms. That's very massive. And the orbital radius of Saturn is 1.4 times 10 to the 12th meters. Okay, the question is, how long does it take Saturn to do one? So we're trying to find the period. What is the period of Saturn? What's the length of time for Saturn to make one complete revolution? Okay, how do we solve this? Well, we solve it using 2 ideas. One, remember, here's Saturn, and right at the center is the Sun. And using this as a simple model, ignoring all the other planets, which would slightly perturb this orbit around, but not too much, we're going to assume we have a circular orbit. So we use Newton's gravitational force of Gm, the Sun, and, the mass of Saturn divided by r squared, and the gravitational force supplies the centripetal acceleration, the centripetal force to the Sun. So the centripetal force to the Saturn's centripetal force is mv squared over r. Okay, so basically which is the centripetal acceleration. So the gravitational force is what supplies the force necessary to keep Saturn going in its orbit. So, okay, notice that the mass of Saturn conveniently cancels out. Notice that one of these radiuses cancel out with one of these, and we are immediately left with g times the mass of the Sun divided by r equals v squared. Okay, now the v squared, remember v, this is the velocity. Okay, now what is v? V is a distance traveled. It's a distance, the circumference. It's the total distance traveled divided by the period. Basically, it's the distance divided by the time. Okay, so the circumference, assuming this is a completely circular orbit, is 2 pi r. So we have 2 pi r over t. So we can, t is the time, in the time for one complete revolution. So we can substitute this directly into here, and we get 2 pi r over t, whoops, quantity squared. We square that whole quantity. Okay? So this will give us 4 pi squared r squared over t squared equals g mass of the Sun divided by r. Okay? In this case, we want to solve for the period t. So let's put t on the left-hand side. T squared equals, I'm going to move everything else to the right-hand side. Okay? It would be 4 pi squared multiplied by r squared, and become r, but multiplied by r becomes r cubed divided by big G divided by the mass of the Sun. Okay, so I'm going to put this up here. So basically, the period is the square root of all of this over here. Because if I take the square, I want to take the square root. So it's, notice I can pull this. I'm just going to go ahead and pull this out, and I'll put 2 pi. I can go ahead and do that. R cubed over g m, the mass of the Sun. Okay, so there's our little formula for the period of Saturn. So let's substitute in. Notice if you're like me, you like to do all the algebra first, solve for what you need to solve for, and then come up with an equation, and then plug your numbers into the equation. As opposed to, don't plug your numbers into immediately here, because you're going to have to do some algebra first. Okay, so we get 1.4 times 10 to the 12th meters, and I have to cube that, divided by g. Okay, and g is 6.67 times 10 to the minus 11 Newton meters squared kilograms squared, okay, times, whoops, I'm just going to erase this for right now, times the mass of the Sun, 2 times 10 to the 30th kilograms, and I have to take the square root of all of that. Okay. Well, let's go ahead. I'm going to go ahead and calculate this. First, I take, with the way my calculator works, I take 1.4 e to the 12th, and I'm going to cube that. Then I'm going to divide by g. Then I'm going to divide by the mass. Then I'm going to take the square root of all of that. Then I'm going to multiply by 2 and times pi. And I end up with 9.0 times 10 to the 8th. 9.0 times 10 to the 8th, and this is seconds. Okay. By the way, how do I know this is seconds? Can we show that this is in fact seconds? And we could just assume it's seconds, but can we show it's seconds? Absolutely. And this is something you should be able to do. Okay, look at all of these units. We have a meter cubed, like a Newton. What is a Newton? A Newton, remember, a Newton is a kilogram. 1 Newton is a kilogram times meter per second squared. So what we have is we have a kilogram meter per second squared times meter squared divided by kilogram squared. Okay, times kilogram. Okay, and we have to take the square root of all of that. Okay, notice that these 2 kilograms cancel with those kilogram. Okay, we have meter times meter squared, that becomes meters cubed. These meters cancel out, leaving you with 1 over second squared, which is the same thing as second squared square root, which all comes out to seconds. Okay, so the units do come out to seconds. Now, how would you convert this to years? This is the right answer, but let's convert that to years. Well, there's 60 seconds in 1 minute, right? 60 minutes in 1 hour, okay? 24 hours in 1 day. Let's see, notice that the seconds will cancel out. Notice and then the minutes will cancel out, and hours will cancel out, so we're up to days. How about a year? 365 days equals 1 year, and the days will cancel out. And so if we multiply this all through, we'll convert this to years. So that will be 9 times 10 to the 8th seconds. Okay, divided by 60, divided by 60, divided by 24, divided by 365, and I get 28.5, or round up to 29 years. So the period of Saturn is 29 years, well, 29 Earth years. Okay. So I hope that's clear in how to solve that rather lengthy problem. Okay. Okay, number 8. Okay, the orbital period of Io, I hope I'm saying that right, Io, one of Jupiter's moons, is 1.77 days. So it gives you the period of Io is 1.77 days. That's days around, that's the moon, Io the moon, around Jupiter. Here's Jupiter in the middle, and here's Io. So it's the orbital period around Jupiter. And that's 1.53 times 10 to the 5th seconds. Okay, if Io orbits Jupiter at a radius, it gives you the radius of 4.22 times 10 to the 8th meters. What is the mass of Jupiter? So you want to know what the mass of Jupiter is. Okay, so how do we solve this one? It's very similar to the last time. The centripetal acceleration, which is the mass of Io times the velocity squared over r, is supplied by the gravitational pull between the two, which is g mass of Jupiter times the mass of Io divided by the radius squared. Notice that the mass of Io immediately cancels out. Again, one of these cancels one of those. Again, we want to solve for the mass of Jupiter. Okay, so we will get v squared times r divided by g. Okay. Is that right? That's right. We multiply by r and divide by g. Okay. But what we have here is the period. We have r, we have the radius, we don't have the velocity, but we have the period. So we can substitute in, because we know that the velocity is the circumference, 2 pi r divided by the period. Okay, so we will say that if I do 2 pi r over period, and I square that, multiplied by r, divided by g. And can you see this? I think so. So we get, notice we have 4 pi squared r cubed, but we have r squared times r, divided by the period squared divided by g. And that equals the mass. Okay? So we should be able to plug all of these numbers into here in order to get what the mass of Jupiter is. Okay? So I'm not going to do it. I'm going to let you go ahead and do it. But this is how I would at least set up the problem. The mass of Jupiter should come out to be, according to what I have here, let's see. Mass of Jupiter. I think I wrote it down wrong. According to the front of the book, the mass of Jupiter is 1.90 times 10 to the 27 kilograms. That's according to the front of the book, the mass of Jupiter. So you can see if you plug this in, if in fact that's actually what you get. Okay. right, number 9. Actually, number 9 and number 10 are all kind of similar, working with the same kind of concepts. Very interesting questions. A satellite orbits the Earth, and it gives them the mass of the Earth with the speed of 1,123 meters per second. What is the orbital radius? So it gives the mass of the Earth of 5.98 times 10 to the 24 kilograms, and it gives that the velocity of the satellite is 1,123 meters per second. And the question is, what is the radius? What is the radius? Okay. Of the radius of this orbiting satellite. Here's the satellite. Again, here's Earth. The centripetal force of the satellite, m of the satellite times v squared over r, is supplied by the gravitational force between the satellite and the Earth, which is g mass of the Earth times the mass of the satellite over r squared. Again, the mass of the satellites cancel out. One of these r's cancels out, and we want to solve for r here, so I'm going to move this radius to the left-hand side, and then we'll get g times the mass of the Earth divided by the velocity squared. Okay, well, let's go ahead and just plug into that. And we get 6.67 times 10 to the minus 11 Newton times meter squared kilogram squared times the mass of the Earth, 5.98 times 10 to the 24th kilograms, divided by the velocity squared. And they give you the velocity, and you have to square that. So that radius, let's see, would be, I take g multiplied by the mass of the Earth, and I divide by 1123, I have to square it first, and I get rounded off to 3 significant figures, 1/6 times 10 to the 8th meters. Okay, so that would be the radius. Okay. Now, for the last question, number 10, I think it's something similar. Okay, a satellite orbits, this is number 10. A satellite orbits the Earth at an altitude, here's the Earth, and here's the center, and the satellite is out here orbiting, beep, 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 beep. Here's the satellite, orbiting with an altitude, that distance there, of 2,314 kilometers. What is this? And it gives, let's see, it gives the mass of the Earth, excuse me, no, well, it does give you the mass of the Earth, 5.98 times 10 to the 24th kilograms, and it gives the mean radius of the Earth, which we'll need, of 6.38 times 10 to the 6 meters. Okay. Well, this is the very same kind of question here, where basically the the centripetal acceleration of the satellite, mass of the satellite, times v squared over r, is given or supplied by the gravitational force, mass g, mass of the Earth, times the mass of the satellite, divided by r squared. And the question is, find the period of the satellite. Okay, how fast the satellite will find that period. So the mass of the satellite, again, cancels out. One of these radiuses cancel out. Okay, and we're left with v squared equals g, mass of the Earth, divided by r. And again, v, the velocity, is the circumference, 2 pi r, divided by the period. So I can substitute that directly into here, 2 pi r over the period, and I have to square that. Okay, so, and I want to solve for the period. So I have 4 pi squared r squared over t squared equals g me over r. Okay, I'm going to solve for, I'm going to put the t on the right-hand side and everything else on the left-hand side. So I will end up with t squared equals 4 pi squared r squared, but I'll move that r over here, so I have r cubed, divided by g, mass of the Earth, divided by mass of the Earth. Okay? So, notice, okay, now we can start substituting in. Now, notice, however, we have to be a little careful here, because the radius of the Earth is only out to here. We have this altitude here also. So basically, the radius all the way to here is the radius of the Earth plus the altitude of 2,314 kilometers. That's kilometers. So the actual radius we're dealing with here is 6.38 times 10 to the 6 meters. And we have to add to that this, which is, this is the same as 2,314, and we have to add 3 more zeros, 0, 0, 0, to put it into meters. Okay? So that's the same thing as 2.314 times 10 to the 6. Okay, so we add to this 2.314 times 10 to the 6 meters. Okay, hopefully that makes sense. This is the radius of the Earth, but this is the altitude that we're above the radius. Okay, that makes sense? So we have to add that. This is 10 to the 6, and we have 4. I'm just adding by hand, 9, 6.8. So our actual radius that we have to plug in is 8.694 times 10 to the 6 meters. Okay. So we're going to plug that into here. I'm going to erase this right here. So our period equals, again, 2 pi, when I take the square root of r cubed divided by g me square root of. Okay, so this is 2 pi, and radius is, again, 8.694 times 10 to the 6 meters, and I have to cube that, divided by 6g, 6.67 times 10 to the minus 11, Newton times meter squared divided by kilogram squared, divided by the mass of, which is 5.98 times 10 to the 24 kilograms. And we have to take the, I'm going to erase all of this over here, and we have to take the square root of all of that. Okay, hope that's not too messy. Okay, so we'll take the radius first, 8.694 e to the 6th. I'm going to cube that. Divided by g, 6.67. And then I divide that by the mass of the Earth. Now I take the square root of that, and I multiply by 2 and pi. And I get 8.065, and the units would be seconds. Doesn't sound like too many. Let's figure this out. 60 seconds is 1 minute.